Hey guys, welcome to the first video in the statics series. In this video, we're going to be looking at two forces in two dimension. So here we have a problem where we have two forces. The first force is pointing in the first quadrant right over here. It has a magnitude of 800 pounds, and there's this angle associated with it, which is 40 degrees. Our second force is pointing right over here in the fourth quadrant. It has a magnitude of 500 pounds and this angle of 30 degrees associated with it. So what is the resultant force? We want to solve for the magnitude and direction of this resultant force. So I'm going to write that down. Our objective is to find the magnitude and direction of the resultant force. Now, the main thing about statics problems is understanding what is going on. And to do so, we do our first step, which is drawing a free body diagram. So free body diagram, that's our first step. And the shorthand notation for a free body diagram is FBD, which stands for free body diagram. So we're going to take our center, our origin, which is our system, and we're going to draw our two forces acting from it. I'm going to label this force 1, and I'm going to label this force F2. So this vector, this arrow over here, is force 1, and this one over here is force 2. Now, it doesn't matter which one's force 1 and force 2, as long as you're consistent. So if this is F2, then this would be related to F2, and this would be related to F2. But now that we have F1 over here, we know that 800 pounds and the 40 degrees angle relates to the force 1. Okay, now let's go ahead and continue drawing our free body diagram. So looking at the origin right over here, we know that our first force points in this direction, and our second force points in this direction. And that's it. Now we just have to label, so we can label this as force 1 and the green as force 2. With our free body diagram complete, we can go ahead and get some equations. So what equations do we need? We need components. So we can't simply add 800 plus 500 to get our resultant because they're not pointing in the same direction. If the arrows were parallel, then yes, we could do that. But because the vectors or the forces are not pointing in the same direction, we have to take their components. So step 2 would be obtaining components. Components. So for force 1, let's look at our first force, which is force 1. We have two components, the force in the x direction and the force 1 component in the y direction. So what do I mean by that? So this is the force in the x direction, and then this is the force in the y direction. Adding these two up, you're going to get the force 1. So how can we get F1x, which is this right here? To do so, all we have to do is take the magnitude, which is 800 of force 1. So F1x equals 800 pounds times, we have this angle over here. So how can I get this, or this magnitude right here? So what we can do is that we know that a right triangle is 90 degrees. And we have this angle of 40 degrees here. So therefore, this angle over here should be 50 degrees to add up to 90. So this creates a 90 degree because we have the y and the x coordinate lines, the axis. So what we're going to do from there is make that 50. And from there, we can go ahead and understand that cosine is adjacent over hypotenuse. So this would be cosine sine 50 times 800 pounds. So to get to our f1 of x, we just multiply 800 times cosine 50, and that should give us 500. So this would be 514.23 pounds. Okay, so that is our f1 of x. So I'm just going to highlight that so we can come back to it. And then for f1y, we know that it's going to be our magnitude times, and we want the opposite from the angle. So that's going to be the sine of 50. So 800 times the sine of 50 is going to give me 612.84 pounds. And it's important to maintain our units. In this case, it's pounds. So now we have the components for the first force. Now we need the components for the second force, which is this force over here. And we're going to do the same thing. So we have force 2 equals the force in the x component, comma, the force in the y component. So to get the x component right over here, we are going to do f2x equals f2, which is 500. We're going to take the magnitude. So 500 pounds times, we have this angle 30, and that is adjacent to the x-axis right over here. So what we're going to do is we're going to say cosine, because cosine is adjacent over hypotenuse, cosine of 30, and when we calculate this, we're going to get that 433.01 pounds. And this is in the x component. So for the y component, we're going to do the same thing. F2y equals the magnitude, which is again 500 pounds. 500 pounds times the sine, because we want the opposite from the angle. So we want this line over here, the y component, and that's going to give us sine of 30. Now, it's important to note that f2y is in the negative y direction. So remember how I said that our force 2 is in the in the fourth quadrant. It's important to note that the x value is positive and the y value is negative. So to account for this, we're going to put a negative sign right over here. And when we calculate this, so for negative 500 times sine of 30, we're going to get negative 250. So minus 250 pounds. Okay. So now that we have our components, we can go ahead and add them. So add components. So step number 3, add components. And to do that, all we're going to do is add the x's and the y's together. So fx, comma fy. This is going to be what our resultant force vector looks like. And to obtain that, all we're going to do is add fr equals f1x plus f2x, comma f1y plus f2y. So f1x, going back over here, we know is 514.23. 514.23 plus f2x, which is right over here, is 433.01. 33.01, and this would give our x component. And for the y component, we're going to add 612.84, which is F1Y. So 612.84 plus negative 250 for F2Y. We're here. And when we calculate this, so when I do 514.23 plus 433.01, I get 947.24. And then if I calculate 612.84 minus 250, or plus negative 250, I'm going to get 362.84. So these are the components for my resultant force in pounds. But the question's asking us to obtain the magnitude. And to obtain the magnitude, I have this vector. Which looks, I'm going to draw this on my plane right here. I'm going to have, so I have an X and I have a Y, just right about there. So this is what my resultant force looks like right over here. Make that this way. So how can I get that resultant, the magnitude? Well, all I need to do is Pythagorean theorem. So where I'm going to label this as A and this as B. So we know that Pythagorean theorem states that C equals A squared plus B squared square rooted. So, and if C is really the magnitude of my force vector, so the magnitude is denoted by these absolute value signs. So going from there, if I take the magnitude of this, so I'm going to have A, which is 947.24 squared, plus 362.84 squared, and take the square root of that. So let's plug that into our calculators. We're going to get 947.24 squared plus 362.84 squared is going to result in 1,014.35 pounds. So this is the magnitude of our resultant force. So I'm going to write that down. So we have the resultant, or magnitude of resultant. Magnitude of resultant. Now, we also need to find the direction. So drawing our components, so we have our FRX, which goes this way, and our FRY, which goes this way. And lastly, our FR, the actual the resultant force, which points in this direction, and what we calculated to have a magnitude of 1,014.35 pounds. We need to find this angle theta. And to do so, what we can do is take the tangent. So tangent is opposite over adjacent. So tan theta equals FR y, which is opposite. So FRY over FRX, which is adjacent to the angle. So doing so, we know that FRX is calculated over here as 947.24. So tan theta equals us 362.84. So 362.84 divided by FRX, which is F1x plus F2x, which gives us 947.24. So 947.24. And then if we take the inverse of the tangent, so tan inverse of 362.84 over 947.24. We plug that into our calculators, and we're going to get 20.96. 6 degrees above the x-axis. So this is our direction for the resultant force. Thanks.